Studying like J flow, and then he also studied the Ricci flow, Ricci flow. So I think also some also the multi-pair equation. So he has been doing expert in this area. So again today he's talk. He also just arrived this morning 4:30. I'm sorry to put him in. He's working so hard. So his talk will be Ricci flow. So they will come back.
Thank you. Well, thank you for the organizers for inviting me. It's really a pleasure to be back here. So, so I was asked to talk about the Ricci flow. I'm going to. I was also told that many people here have seen lots of lectures on Ricci flow, and on the other hand, I suspect that some people are not very familiar. So I'm going to at least begin in a very introductory way. But then hopefully I'll cover something which is a little bit new for at least everyone. So, but today my goal is really some basics about Kähler manifolds, the notation I'm going to use, and so on, and a kind of overview of the Kähler-Ricci flow, especially in the case of Kähler surfaces. So I'm going to write KOF for Kähler-Ricci flow on Kähler surfaces. Namely, so these are complex manifolds of complex dimension 2, so real four-dimensional manifolds which admit Kähler metrics. And what we're going to see is that actually, in contrast to the Riemannian Ricci flow, which was discussed this morning by a video, is that there we know almost nothing about what happens to the flow in general, but it turns out for the Kähler-Ricci flow you know almost everything. I mean, at least there are still some open questions left, but there's not really that many surprises left. Okay, so to begin with, then let me start with just some background on Kähler metrics and Kähler manifolds. So let me start from the beginning. Let's suppose we have M is a compact complex manifold, and I'll suppose it has complex dimension n. And so we have local coordinates, local complex coordinates, z1 up to zn, and I can write zi as xi plus root minus. I prefer root minus 1 instead of I. Root minus 1 yi, and then so the real coordinates, then you have x1 up to xn and y1 up to yn. And we know, of course, that the tangent space at a point on my manifold, locally I can think of this as the span of the vectors ddx1, ddxn, and ddy1, ddyn. It's a real 2n dimensional manifold. But since we're going to be working on complex manifolds, we prefer to use the complexified tangent space. And this means that I would take the span over the complex numbers. But I don't want to use these vectors. Instead, I'm going to use the more natural complex vectors, which are ddz and ddz bar. So I can write this as ddz1, ddzn, plus the span over the complex numbers of ddz1 bar, ddzn bar. And this I'll call T10. Sorry, maybe that's hard to read. And this I'll call T01, maybe with an M. I guess this is all at a single point. And this decomposition is independent. So I wrote everything in terms of these coordinates, but That decomposition is independent of the choice of coordinates. And what do I mean by this ddzi? So here I mean when I write ddzi, I mean 1/2 ddxi minus root minus 1 ddyi. And ddzi bar would be just the conjugate of that. So these are complex vectors. Okay, so what is a metric? So let me start with a Hermitian metric. So a Hermitian metric, if I go with the shadow here, okay, a Hermitian metric, G is by definition, it's simply an inner product, a Hermitian inner product. It's a Hermitian inner product on this complexified, on this T10. I guess let me put a P there, and that's for each P, where P is a point on my manifold, and it should be varying smoothly in P. And of course, such metrics always exist. Locally, how do we write this? So locally, I would write such a metric as a. So this is just a copy of Cn, and so Hermitian inner product will be given by n by n positive definite Hermitian matrix, which I'll write as Gij bar. And then if we're given two vectors, say x, y, which are T10 vectors, then the inner product of x and y with respect to G would be Gij bar xi yj bar, where of course I'm summing in I and j. Where here, of course, I'm writing x as xi ddzi, and y is yi ddzi. Okay, so this is what I'm thinking of as a Hermitian metric on my manifold, and as I said, these, of course, exist in abundance. That's not always the way that you would see a Hermitian metric introduced. Sometimes perhaps it's more standard to start with a Riemannian metric and say it has certain properties. But you can start in this way, and the G determines so let me just mention it. The G, of course, determines a Riemannian metric. And the way to see that would be that you could define G of ddzi, ddzi bar, just to be Gij bar, and define capital G of ddzi, ddzi to be 0, and this call is ddzi bar, ddzi j bar, and then this G, capital G, would be a symmetric bilinear form on the complex tangent space. So G would be a map from TMC plus TMC to C. And then you would, when you restrict it to the real tangent space, you get a Riemannian metric. So you restrict to TM, and you get a Riemannian metric. So that would correspond to the other way of thinking about a Hermitian metric. Okay, so this is just Hermitian metrics, and as I said, they always exist. But now let me give a definition. So given G Hermitian, we define a real 1-1 form. Let me call it omega, to be root minus 1 Gij bar dzi wedge dzj bar. And I'm going to divide by 2 pi. It just turns out that this is convenient for later. So I'm going to always divide by 2 pi, although sometimes I might forget. And this is a real one-one form. Why is it real? Because when you take the conjugate from the root minus 1, you get a minus sign. Here, this is a Hermitian matrix. So when you take the conjugate, it will become Ji bar. And then here, you'd have to switch them again, so you get another minus sign. That's why you see that it's real. And then the definition is that we say that G is scalar if d omega is 0. And in particular, omega is a symplectic form. Right. And omega is called the scalar form. It's called the scalar form, but it's typical to call omega a scalar metric, and I'll often do that. Okay. Let me give some examples. So this is all very basic stuff so far. So of course, if the dimension of M is 1, in other words, it's a Riemann surface, then of course every Hermitian metric is scalar. Every Hermitian metric is scalar. And that's just because omega is a 2 form, so take d of it, you're going to get 0 on a manifold of 2 real dimensions. Second, CPN is a standard example. So let me write CPN, or simply PN, is another example of a scalar manifold. You take Cn plus 1, take away the origin, and then you quotient out by saying that Z naught Zn is equivalent to, say, lambda times Z naught Zn, where lambda is a non-zero complex number. And we're going to see CPN rather a lot. You have coordinate charts U0, U1, and so on. Okay, so let's call them U alpha, say, which is Z alpha is non-zero. And there's a well-known metric, which is the Fubini-Studi metric. So this is the so-called Fubini-Studi. The Fubini-Studi metric. And let me define what it is in the case, in local coordinates. So on U1, I can write it as root minus 1. Again, I'm going to divide by 2 pi. Log of 1 plus Z1 squared plus Zn squared on U0, where I'm going to take my Zi to be Zi, the capital Zi, divided by Z naught. And similarly on, and etc. You can define it similarly on the other coordinate charts. And you can clearly see that this is closed because it's in fact it's dd bar exact. So certainly it's closed, and it takes a little bit more work to check that it's positive definite. Okay. And then the third example is you could take any M in PN, in CPN, a complex submanifold. In other words, well, these are, by Child's theorem, this is the same thing as all smooth projective varieties. So any smooth projective variety admits a scalar metric because you take omega, you take the Fubini-Studi metric and restrict it to M, and this is scalar. Okay, so that's sort of these are the basic objects of algebraic geometry. So this is, of course, an important class of examples. Okay, last example is a non-example. So let me give an example of a manifold which doesn't admit a scalar metric. So number 4 is a non-example. You can take M to be the Hopf surface. So what I do is I take C2 minus the origin, and I quotient out by the relation Z1, Z2 is equivalent to 2 Z1, Z2. Okay, notice the difference here with the CPN is that here I was allowing lambda to be any positive complex number. Here I'm specifying a single one. This is a compact complex manifold. And in fact, you see that M is diffeomorphic to S3 cross S1. And it's not difficult to see that because you can map, you can take Z1, Z2 in M and send it to, let me call this Z with an underline. Just send it to Z divided by the length of Z, where I think of this as being inside R4. And then the length of Z, where this is now going to be in, this is an element of, I could think of this is a unit vector now in R4, so I can think of it as an element of S3. And this is just a real positive number, but it's only defined up to factors of 2, so I have to sort of quotient out by x goes to 2x, but this is just a copy of S1. So this gives you a diffeomorphism, and you can see then that it cannot be Kähler, so this is not, has no Kähler metric. And why is that? Well, so some basic topology tells you that since this has no H1, so it's simply connected, it tells you the product has no H2. So H2 of M is 0, and but on the other hand, a Kähler metric omega is in fact in particular symplectic form. It's closed, and it's certainly non-degenerate because when you take the top power, you get the determinant of G. The Kähler metric is a symplectic form. So it gives you an element of H2, which is non-zero. So that's the simplest example, I think, of a non-Kähler complex manifold. So there's certainly plenty of examples of non-Kähler manifolds, but I'm not going to be really talking about that today. Okay, so let me now talk about the Kähler-Ricci flow. So all of this was just basic. Sorry, was there a question? So I want to start now talking about the Kähler-Ricci flow, which is the main, which is the main topic I want to talk about. Okay. So hopefully most of this is familiar stuff. So what is the Kähler-Ricci flow? So let's take M omega naught now to be a compact Kähler manifold. Then we say that a smooth family. So a smooth family. Let's call it omega t for t in 0 to capital T, where capital T is some number which is strictly positive and could be infinity. Is a solution of the Kähler-Ricci flow, which I'll write as KRF. It's the solution of the Kähler-Ricci flow starting at omega naught if omega 0 is equal to omega naught, and ddt of omega is minus the Ricci of omega. So that, I guess this is omega t. Minus Ricci of omega t. This is, of course, on for t and 0t. Where, what is this Ricci? So here I'm writing Ricci of omega for, again, there's going to be some factor of 2 pi. Of dd bar log of the determinant of g. So here, so for any calorimetric omega which is given by a g, Ricci of omega is minus dd bar log of determinant of g. Okay. So that's a solution of the Kähler-Ricci flow starting at omega naught. And this, so notice this is a, that the Ricci of omega is a closed, certainly closed, because again d of something which is d exact is always going to be closed. It's a closed it's a closed real 1-1 form, and it does correspond indeed to the Ricci curvature of the corresponding Riemannian metric. So we're not really talking about those Riemannian metrics, but it does correspond to that. So it really is the Ricci flow. The only difference with the Ricci flow is that Ricci flow usually put a 2, and we don't put a 2 here. Okay, so this is the Kähler-Ricci flow. And let me say a few words about it. So a key theorem to begin with is that the behavior is that this capital T, well, the maximal capital T is determined by cohomology. Okay, so the maximal capital T is determined rather easily by cohomology. So by the topological data. So let me explain that. So given omega, omega Kähler, I can look at the cohomology class in what I'll call, I'm going to use Dolbeau cohomology. So let me write it like this. So this is H11 d bar m r. I'm going to just tend to write it just as H11. What is this space? Well, I'm going to define this to be, I mean, there's some equivalent definitions, but I'll define this to be, just say the d bar closed real 1-1 forms quotient out by the image of d bar. Well, omega being Kähler is not just d bar closed, but is d closed, a straight d closed. But those are actually the same things. It's not difficult to see just by looking at degree that if you're a real 1-1 form, if you're d bar closed, then it's the same as being d closed. And this is the same as, so by the dd bar lemma, so this is a non-trivial result, which holds on Kähler manifolds, which is that you can say this is the same thing as saying d bar closed, or I could write just straight d closed. D bar closed, real 1-1 forms. Quotient out by the image of dd bar. In other words, by dd bar of a function, just a function. So note in particular. If omega and omega prime are both are Kähler metrics in the same cohomology class, so let me just say that they're in the same cohomology class, then omega prime I can write as omega plus dd bar of a function phi, and let me divide by 2 pi just for convenience, for some real valued function, phi, and moreover phi is unique up to the addition of a constant. up to the addition of a constant. Of a constant. Okay, so now let me say something a bit more about this. I want to define the Kähler cone. So we say that an element alpha in H11. Let me write H11 for this space. That alpha in H11 is a Kähler class. If it contains a Kähler metric. That's a pretty obvious definition. If it contains a Kähler metric, and we write, I'm just going to write alpha is positive. So when I write alpha positive, that means that it's a Kähler class. And then we make a definition, so we define the Kähler cone, which I'll write as Ka of m, simply to be the set of alpha where alpha is positive. And that's a cone in the sense that take any two elements and add them up. Clearly that's also going to be in the cone, right? Because add up two Kähler metrics is still going to be Kähler. Similarly, take any element here, multiply by positive constant, again it will be in the cone. So it's a cone in that sense, in that usual sense. So let's now go back and look at the let's look at the Ricci flow, Kähler Ricci flow. So given a solution omega t of the Kähler Ricci flow, let's call it. Let's write star here. I can take the cohomology classes, and what I see is that the ddt of omega t, this is now just an element of a finite dimensional vector space, is equal to minus the cohomology class of Ricci of omega t. So I've said already that this is a closed real 1-1 form, so it's an element of H11. Sorry, no, I shouldn't write that. Its cohomology class is an element of H11. So let me. In fact, it's a rather special one. This it's called the first Chern class. So this is the so-called first Chern class. So the first Chern class I can take by definition is simply the Ricci curvature of omega for any metric omega, for any Kähler metric omega. And what I notice is this is the cohomology class itself is independent of the choice of omega. And so note that C1 of m is independent of omega, depends only on the manifold. And the reason is rather simple. Why is it? Because if you took, so let me just put in parentheses, if you took the Ricci of some other metric omega prime, this would be minus dd bar log with some factor of 2 pi, which I may forget at some point. This is determinant of G prime. But the determinant of G prime is just locally just a function, right? So if you look at the quotient of determinant G prime and determinant G, that's just a globally defined function on the manifold. So the difference is some e to the f. For some function f, which is, so e to the f is just defined to be this determinant divided by this. And then this is just the Ricci of omega, this is just the Ricci of omega minus dd bar f, again divided by 2 pi. And so that tells me that the cohomology, so they differ by something dd bar exact, so they're in the same cohomology class. Okay, where am I going? Maybe I'll go over here. Right. So maybe I'll push this one up. So what we see is that that the Kähler-Ricci flow moves in a certain direction. So what we see is that the ddt of omega t is just minus c1 of m. So we see that ddt of omega t is minus c1 of m. And this is independent of t. So in particular, it says that omega t, the cohomology class, so I know that it starts at omega naught, and then it just moves linearly in the direction of minus c1 of m. Okay, so as long as the flow exists. As long as the flow exists. If I draw a picture, here's the Kähler cone. I'll draw it as a cone. It's a finite dimensional cone in Rn. And then what we start with some omega naught. And let's say that C1 of m is, say, in this direction. So that would be telling me that the Kähler-Ricci flow would move in this direction. Okay. So the main theorem says that. So what we notice is that, of course, this is a Kähler class, right? So we notice that this has to be a Kähler in the Kähler cone, as long as it exists, because omega t is a Kähler metric. So I'm assuming I have a solution of the Kähler-Ricci flow, and therefore this cohomology class is represented by a Kähler metric, therefore it's positive, so it's in the Kähler cone. And then the theorem says that actually all you have to do is just look at the first point where you leave the Kähler cone, and that tells you the maximal existence time. So this theorem goes back to the original work on the Kähler-Ricci flow, which is due to Huaidong, and but this so he proved this in the special cases of C1 positive or 0 or negative. For the more general case, it's due to Suji. Again, did some slightly more general cases, and this final result is due to Tian Zhang. So they said that they show that there exists. So the maximal existence time. So the maximal existence time, capital T, is simply given by the formula. That capital T it's simply the supremum of T positive, such that this omega naught minus T C1 of m remains in the Kähler cone. In other words, that's a positive element of H11. So as long as we stay in the Kähler cone, then actually there exists a solution of the Kähler-Ricci flow, and moreover, the flow is unique, and the solution is unique. What do I mean by maximal existence time? I mean, there's no bigger time for which you can have a smooth solution. So as you approach capital T, assuming that capital T is finite, then you would have to have a singularity. Okay. Let me just note that of course T is equal to infinity is certainly possible. And that would occur, for example, if C1 of m, if minus C1 of m was positive, or in other words, C1 of m is negative, because you see in the picture, minus C1 of m with negative, so say it looks like this. So it's a C1 of m, and then you see that that omega t, you can see it's never going to leave the Kähler cone. Of course, you could also take C1 of m as 0, and then it's also trivially true that this would, capital T would be infinity. The most general result would be you take if you take minus C1 of m on the boundary of the Kähler cone, and then that's also called Neff classes. Then that would also give you existence for all time. Okay. So let me say something about the simplest case, and that is the case of Riemann surfaces. So this is familiar to people who study Ricci flow. Let's look at the first of the case of Riemann surfaces. And then we'll move on to the more interesting cases of Kähler surfaces. So in this case, let's take the dimension. So we take the dimension, the complex dimension is 1. So in this case, we know by the uniformization theorem that every such manifold admits a metric of constant curvature. So M admits a metric omega with constant curvature, which is the same thing as in one dimension. All the curvatures are basically the same. The same thing as saying the Ricci curvature is constant, or the Ricci curvature is mu times omega with mu a constant. And in particular, I could take mu to be 1, 0, or minus 1 after scaling omega. You notice that the Ricci curvature doesn't change when you scale omega, so I can always achieve that. And we know that the case mu is 1 is the positive curvature corresponds to the sphere, topologically the sphere. Mu is 0 corresponds to a torus, and mu is negative 1 would correspond to a surface of higher genus. Okay. The case of dimension 1, the Kähler cone is not very interesting. It's just one-dimensional. So in this case, the Kähler cone is so here the Kähler cone is a half line. It's just one-dimensional. If you're in the case mu is 1, you see that C1 of m is positive. And in this case, you see that capital T is finite, and it's simply given by omega naught. It's where you have this is equal to 0, so it is equal to capital T times C1 of m. So it would be given by that number, capital T. It would be finite. So capital T is finite. And again, by scaling omega naught, let's assume by scaling omega naught, the initial metric, let's assume that capital T is 1. So what we see in this case is that the maximal solution of the Kähler-Ricci flow exists on time 0 to 1. So in other words, it doesn't exist more than 1 second, if you like. There's a singularity. But on the other hand, it turns out that when you rescale the flow, it actually converges to a nice Rubini-Studi metric on the sphere, on the P1. So in fact, given omega t, solving the Kähler-Ricci flow, starting at omega naught, so omega 0 is omega naught, and ddt of omega t is minus Ricci of omega t, it makes sense to rescale. So you renormalize. You renormalize. And what you can do is define omega tilde s. I have a new time variable s, and I can do it like e to the s, omega of 1 minus e to the minus s. And when s is 0, you see that this is omega of 0, so it's still omega naught. But now when you compute dds of omega tilde s, then you get just e to the s times this, which is the same as omega tilde s, and then plus e to the s times ddt of omega at 1 minus e to the minus s times this, which is e to the minus s, which cancels that e to the s. But then this is nothing other than the Ricci curvature, or minus the Ricci curvature of this guy, which is nothing other than omega tilde. Because I can ignore the scaling when I compute the Ricci curvature. And then you see that the cohomology class of this doesn't change. Because initially, the cohomology class is equal to C1 of M, and it'll remain so. So the volume will stay the same. Well, in this case, yeah, if you integrate the metric, it's just given by the cohomology class. So the volume stays the same. Okay, so in this particular case, it makes sense to do that. And then actually S now will go from 0 to infinity. And it's a well-known theorem of, so it's a well-known theorem of Hamilton and Ben Chow. So Ben Chow did a remaining case that as s goes to infinity, this normalized flow omega s converges to omega, say infinity. This is smoothly where Ricci of omega infinity is equal to omega infinity. Okay. So that's the case mu is 1. Let me just briefly mention the other two cases. Mu is 0. You don't have to do any normalization. Again, Hamilton showed that omega t will converge to omega infinity with Ricci of omega infinity is 0. So this is as t goes to infinity, so the flow will exist for all time. And then the final case is when mu is minus 1. And then again you consider renormalization. So we consider instead the renormalized flow, which is in this case ddt of omega is minus Ricci minus omega, and then again then omega t will converge to omega infinity as t goes to infinity, where this Ricci of omega infinity is minus omega infinity. Okay, so again this is Hamilton. And yeah, these two cases also, I mean, follow from Hyde and Tsau's work. That will give it another proof of those. Okay. So the case of Riemann surfaces, basically, there's no bad behavior. The worst case is the case of mu is 1, where you see it getting a singularity, but actually when you rescale, you see there's no singularity at all. So now what I want to do, well, I'm running out of time, so maybe in the next hour, what I want to talk about is the case of Kähler surfaces. So this is complex dimension 2. And as I said, actually we know an awful lot about what happens. We really have a very good general picture of what happens. Why are we interested in it? Well, one reason is that we're very interested in the Ricci flow in 4 dimensions. As I said, beyond the Kähler case, I mean, there's been a lot of progress in solitons, as we've seen from the last lectures. But still, we're a long way off from understanding what happens in real dimension 4. The other reason is that there's a connection between the Kähler-Ricci flow and algebraic geometry via the so-called minimal model program. And so we're interested also in possible connections with algebra, and maybe the Kähler-Ricci flow can tell us something new about algebra, who knows. Okay, maybe that's a good time to stop, and we can start again in 10 minutes.